There is a sky above you that is very slowly emptying. Not tonight, and not for billions upon billions of years. But somewhere in the deep arithmetic of the cosmos, the distances between things are widening, a little more with every passing breath of time, and there is a place where that widening might one day end. A place where a single star would lose sight of every other star, where the last galaxy you could ever glimpse slips past the edge of the visible, where even the atoms that make a hand or a held breath would loosen their grip on one another and drift apart into the dark. Picture it from a great and painless distance, a final brightening of the whole sky, the gentlest possible undoing of everything that was ever held together. There is a name for that imagined ending. It is called the Big Rip. And what is it like for a universe to let go? You do not need to hold any of this. There is nothing here to study, nothing to memorize, nothing to keep. Let the ideas pass through the way warm air moves through an open window, touching you for a moment, then drifting past, asking for nothing in return. Some of these wonders will stay with you into sleep, and some will dissolve before morning, and either way is exactly right. This is the strange comfort of the very large and the very far. It has already outlasted everything that ever worried over it, and it will go on whether you remember it or not. So let the mind go loose. Let the eyes grow heavy if they want to. The cosmos is in no hurry, and tonight, neither are you. Begin close, with a thing you have felt without ever being told. When you look up at the night, the stars seem fixed, eternal, pinned in place like frost on dark glass. They are not. Every galaxy beyond our own small neighbourhood is drifting away from us, and the more distant it is, the faster it goes, as if the whole of space were a dark fabric being stretched in every direction at once. You're not at the centre of that stretching because there is no centre. Each point moves away from every other point, the way raisins set in rising dough drift apart not because they travel through the bread, but because the bread itself swells between them. The universe is the dough, the galaxies are the raisins, and the rising has been going on for 13.5 billion years, silent and unstoppable, beneath every night sky that any creature on this world has ever seen. That swelling has a measured pace, and a single number captures it. Across every stretch of empty space between the galaxies, the cosmos grows by a small, steady fraction every second, and that fraction is called the Hubble constant. It was named for the astronomer who first showed, almost a century ago, that the farther a galaxy lies from us, the faster it recedes. A clean and simple proportion, far away means fast away, that overturned the ancient picture of an eternal, unmoving sky. Before that discovery, the universe was thought to be a fixed and finished thing, the same forever. After it, the cosmos became something with a history and a direction, a thing that was once smaller and is steadily becoming larger. The whole modern story of cosmic fate begins with that one ratio written in starlight. For most of the last century, the great question was whether the rising would slow. Gravity, after all, pulls inward. Every speck of matter tugs on every other speck across the void, and it seemed only reasonable that the expansion born in the first instant of time should be losing speed, the way a stone thrown upward loses pace as the Earth calls it home. Astronomers expected to measure exactly that gradual breaking. They built careful instruments to catch it. The only question, they thought, was whether the cosmos would decelerate enough to halt and fall back together one day, or merely coast outward forever. And either way, the expansion was surely easing. The future of the universe, it seemed, came down to how hard the brakes were being pressed. In the final years of the 1990s, two rival teams of scientists turned their telescopes toward a particular kind of dying star in distant galaxies. These were stellar explosions of a very special type, so uniform in their true brightness that their apparent dimness reveals precisely how far away they lie. Cosmic mile markers scattered across billions of light years. The light from these explosions had travelled for ages to reach the glass, carrying within it a record of how fast the universe was expanding back when it set out. The two teams worked independently, half in competition, each hoping to be the first to measure the great cosmic deceleration. and when their numbers finally came in, the distant explosions were fainter than they should have been. Too far away, too dim, as if something had been carrying them outward faster than anyone had dared to guess. Sit a moment inside that overturned expectation. The far reaches of the universe were not slowing down at all. They were speeding up. Something was pushing the cosmos apart faster and faster, working against all the gravity of all the matter that has ever existed, and winning. It was one of the most unexpected discoveries in the history of science, a result that no one had ordered and almost no one had predicted, arriving quietly on a handful of photographic plates. The universe was not a stone falling back to Earth. It was a stone that, halfway up, had begun to climb on its own. The unknown push needed a name, and the name astronomers chose is really a confession of how little is understood. They called it dark energy. It is not dark the way a moonless field is dark. It is dark the way a sealed room is dark to someone who has never held the key. And it makes up roughly 68% of everything there is, more than 2/3 of the entire contents of the cosmos, a silent, invisible presence woven through all the emptiness, whose single discernible effect is to push space apart. Everything else, all the matter and all the light, every star and world and living thing, accounts for less than 1/3 of the whole. The universe is mostly made of a thing for which there is, as yet, only a placeholder word. That proportion quietly rearranges the sense of the world. Everything you have ever seen, every mountain and ocean, every star catalogued by every astronomer who ever lived, every atom in every living thing, all of it together is the small visible froth on a far deeper sea. Space itself is not the inert, empty stage everyone once imagined. Space has a faint tension built into it, a hidden outward pressure present in every cubic inch of the vacuum, and that pressure is the silent protagonist of this whole long night. The emptiness is not empty, it pushes. The 3 astronomers who first read the acceleration out of their data were named Saul Perlmutter, Brian Schmidt, and Adam Riess, and years later they were given the Nobel Prize in Physics for it. Imagine being among the first humans ever to learn that the universe is not winding down but winding up, that the future is wider and stranger and more luminous with distance than anyone had supposed. They did not go looking for it. They set out to measure a slowing and found a quickening instead, which is so often how the deepest things are found, not by seeking them, but by being honest about what the light actually says, even when it says something no one wanted to hear. The simplest way to describe dark energy is with a single understated number, a ratio that physicists call the equation of state and label with the letter W. It compares the pressure of dark energy to its density, and that one value, more than any other, decides the entire fate of the cosmos. If W settles at exactly -1, dark energy behaves like a perfectly steady tension built into the vacuum, unchanging, identical in every corner of empty space, the same today and 1 trillion years from now. Under that value, the universe expands faster and faster, but it never tears. The galaxies simply draw apart into a deepening dark, gradually, endlessly, across spans of time beyond all imagining. Almost everything the telescopes have seen so far is consistent with W resting very close to that unremarkable number. But measurement is never perfectly sharp, and the value of W is not yet pinned down to its last decimal. It hovers near -1 with a small uncertainty hanging around it like mist, and inside that mist there is room for a stranger possibility. If W were not merely -1 but a little more negative still, a fraction below, then dark energy would stop being a constant. It would become something that grows. The push would intensify as the universe swelled, feeding on its own expansion, a tension that does not stay level but climbs, without limit, toward a single appointed moment. Physicists gave this hypothetical, more aggressive form of dark energy its own unsettling name, phantom energy. And phantom energy is the engine that drives the Big Rip. The difference between these two futures rests in the mind like two smooth stones weighed one in each open hand. In one future, the universe ends in cold and silence and endless coasting apart, a slow fade with no final note. In the other, the expansion sharpens to a point, a crescendo written into space-time itself, and everything ever bound together comes undone in a finite, nameable span of time. The whole question of which stone is heavier comes down to whether one small number is exactly -1, or just a whisper below it. No one yet knows. The cosmos is not told, and there is a peculiar peace in resting inside a question this large and this unhurried. A question that will not be answered in your lifetime, or in 10,000 lifetimes, and so ask nothing of you tonight at all. The Big Rip, as a named idea, is young. Younger than many of the trees outside your window. In the year 2003, 3 physicists named Robert Caldwell, Mark Kamionkowski, and Nevin Weinberg published a short paper with a startling title, Dark Energy, with double doubles less than -1, they wrote, would cause a cosmic doomsday. In just a handful of pages, they worked out what would happen to a universe filled with phantom energy, and they followed the mathematics calmly all the way to its end. The paper is almost clinical, full of clean equations, and folded inside those equations lies one of the most extraordinary stories the cosmos could ever tell about its own conclusion. The whole immense catastrophe, if it is real, was first glimpsed not through any telescope but at the tip of a pencil. What those equations describe is a kind of countdown, not a clock ticking toward an explosion, but a great slow unbinding that begins with the largest structures and works its way patiently inward toward the smallest. To picture how it would unfold, hold on to a single idea about the eternal contest between expansion and gravity. Across small distances, gravity wins easily. The Earth keeps its grip on the Moon, the Sun keeps its planets close, the local bonds hold. Across enormous distances, expansion wins, and galaxies are carried apart. Today the boundary between those two domains lies far out among the galaxies, well beyond any single star. But if dark energy keeps growing, that boundary creeps steadily inward, and everything it passes is set loose. So the countdown opens at its most leisurely, billions of years from now, when the great clusters of galaxies feel the first faint loosening. Today, galaxies gather into vast gravitational families, hundreds or thousands of them bound together across millions of light years, swimming through the same deep tides. Under a growing dark energy, those families would be the very first to dissolve. The bonds between neighbouring galaxies give way, the companions recede beyond reach, and each galaxy is left more and more alone in a widening dark, the lights of its former kin reddening and dimming and finally slipping out of sight entirely. Nothing violent happens in this opening movement. It is only a great and gradual emptying of the sky, structure by structure, a cosmos quietly clearing its own table. Next, the loosening reaches the galaxies themselves. A galaxy is a city of stars, hundreds of billions of them wheeling slowly around a common centre, held in their long orbits by the combined gravity of all the rest. In the Big Rip scenario, that shared gravity would eventually lose its hold. The estimates suggest a great spiral like our own would come apart roughly 60 million years before the very end. The stars no longer orbiting but drifting outward, the graceful arms unwinding into scattered points that recede from one another, the whole luminous pinwheel thinning into the dark until it is no longer a galaxy at all, only stars, alone, falling away from stars. 60 million years sounds immense, and it is. But against the full age of the universe, it is the last thin sliver, the final page of a very long book. Imagine where a single star would find itself in those closing ages. Say, a star much like the Sun, with worlds turning patiently around it. For nearly all of the countdown, nothing would seem wrong at all. The star would shine, the planets would keep their seasons, the local sky would look almost as it always had, only emptier each long night as the rest of the universe withdrew. The growing dark energy is so thin across a region, the size of a planetary system, that, for billions upon billions of years, it makes no difference anyone could feel. The unbinding stays cosmically far away, and then, only in the very last months, would it finally arrive in the neighbourhood of the star, the boundary of expansion sweeping inward at last across the orbits of the worlds. Roughly 3 months before the end, in the careful calculations of that 2003 paper, the dark energy within the empty space of a planetary system would finally overwhelm the gravity that holds its worlds to their star. A planet's orbit is a kind of balance, a falling that never quite lands, the inward pull of gravity matched against the outward sweep of motion. Tip that balance and the falling simply stops. The worlds would loosen from their sun, their bound orbits unspooling into open paths, each planet drifting away into the dark on its own, no longer circling anything at all. A solar system is one of the most stable arrangements in all of nature, turning like clockwork for billions of years on end. In the Big Rip, it would simply gently let its planets go. Smaller still, and later still, the Rip would reach a single world. A planet holds itself together by its own gravity, every part of it pulling on every other part, pressing rock and metal and ocean into a sphere. In the final half hour before the end, the equations say, the growing dark energy inside the planet itself would exceed that self-gravity. The world would begin to come apart, not shattered by any blow, not struck by anything at all, but simply unbound, its own substance no longer able to hold its own shape. Mountains, seas, the very ground underfoot, all of it loosening outward at once, in a silence with no wind in it, because there would no longer be anything able to hold a wind together. The whole long history of a planet ended in the space of half an hour, by nothing more dramatic than space itself growing too insistent to resist, and then the very last instant, the moment the entire countdown has been falling toward, when the Rip reaches into the atom. Matter is mostly empty space. An atom is a tiny, dense nucleus with a vast hush around it where the electrons dwell, bound to that centre by electric force. In the Big Rip, the dark energy would finally grow stronger even than this. The estimates place the moment at the almost unsayable scale of about 10 to the negative 19th of a second before the end, a span so brief it makes a single heartbeat seem to last an age. First, the electrons would be pulled free of their nuclei, then the nuclei themselves, the very protons and neutrons, would be torn from one another, and matter as a structured thing would simply cease to be. There would be nothing left to come apart because the coming apart would have reached the bottom of the ladder. That final figure, a 10,000th of a millionth of a millionth of a second, is the closest the mathematics can carry you to the last edge of time, and it is so small that it is almost a kind of mercy. The whole sequence is a single gesture, run from the outside inward. The clusters first, then the galaxies, then the planetary systems, then the worlds, then the atoms, each scale set loose in its turn as the boundary of expansion sweeps relentlessly down toward the small. It is the exact reverse of how the universe assembled itself in the first place. Structure formed from the inside out, the tiny things first, particles cohering into atoms, atoms gathering into stars, stars assembling into galaxies, galaxies clustering at last into the great cosmic web. The Big Rip would run that whole film backward, unmaking the large things first and the small things last, until the cosmos had quietly returned every building block it ever borrowed and kept nothing at all for itself. A number hangs over this ending, a date of sorts, though an exceedingly soft one. In one of the simplest phantom models with the equation of state set to -1.5, the calculations place the Big Rip about 22 billion years from now. 22 billion. The universe so far has lived less than 14, so even in this faster scenario, the end would lie further ahead of you than the entire past of everything lies behind. More time still to come than has ever yet elapsed since the very beginning. The light leaving distant stars tonight would have ages upon ages to cross the widening dark before any of this began. You're nowhere near the edge of the story. You're barely past its opening lines. That particular figure, though, assumes a value of WW that the real measurements do not actually favour. When astronomers fold in everything they have learned from the faint glow of the infant universe and from the distant exploding stars, the most likely value of WW sits even closer to -1, and the gentlest readings push any possible rip far further out to 150 billion years, 200 billion, or away into a future so distant the numbers lose their grip on the mind entirely. The nearer W lies to that quiet -1, the longer the lease, and the more likely it becomes that the universe never tears at all, but only drifts apart forever in the cold. If the end comes, it has been pushed so far over the horizon that no living thing now in existence will ever stand within reach of it. You can even write the moment of the rip as a formula, and there is a strange beauty in how simple it turns out to be. The time remaining depends on only a few quantities: how fast the universe expands today, how much of it is ordinary matter, and how far below -1 the value of W has slipped. As W approaches -1 from below, the answer the formula gives swells toward infinity. The appointed moment retreats endlessly into the future and finally vanishes altogether. The entire difference between an ending and an eternity is folded into the gap between one number and its nearest neighbour, a difference too fine for any instrument yet built to resolve. Somewhere in that razor-thin band of uncertainty lives the whole fate of all things. It is worth pausing on what an unusual creature phantom energy would be if it truly exists. Ordinary substances thin out as space expands, spread the same gas through a larger room and its density falls. Even a steady cosmological constant holds its density level no matter how much the universe grows, conjuring just enough of itself to fill each new volume. But phantom energy would do something stranger than either. As space expanded, its density would rise. The bigger the universe became, the more phantom energy each region would hold, and the harder it would push, accelerating the very expansion that fed it, in a runaway that climbs and climbs, a thing that grows stronger by spreading thinner. Nothing in ordinary experience behaves this way, which is exactly why physicists hold the idea at arm's length, even as they take its mathematics seriously. That arm's length caution matters because the Big Rip is not a prediction, it is a possibility, one branch among several in the great forking of cosmic futures, and not the branch most physicists would wager on. The honest position is that no one knows how the universe ends, and the not knowing is itself a kind of open window onto wonder. The same data that allow the rip also allow a universe that coasts apart forever, without ever tearing, and allow, at the very edge of the numbers, a universe that might one day even reverse. 3 or 4 entirely different endings all fit comfortably inside what the telescopes have so far been able to see. To rest inside that uncertainty is not a failure of knowledge. It is the live, unfinished edge of one of the oldest questions a mind can ask. Set the rip gently aside for a moment and meet its quietest rival, the ending that most cosmologists today consider the likeliest of all. If dark energy is simply that steady cosmological constant, you're exactly -1 and never growing, then nothing is ever torn. Instead, the universe expands forever at an ever-quickening pace, and the galaxies beyond our own bound neighbourhood slide further and further away, their light stretching redder and redder until it fades entirely below seeing. Star formation gutters out as the gas grows thin. The stars themselves burn down one by one over spans of time that dwarf everything that has yet happened. This long, cold, fading future has a name as plain as the rips is dramatic. The big freeze, the heat death, the slow surrender to darkness and cold. No tearing, only an endless deepening night. Older than either of these, and now thought unlikely, is the ending the ancients might have found most fitting. A universe that stops expanding, turns and falls back in on itself. If gravity were strong enough and dark energy weak or absent, The great outward rush would one day slow, halt, and reverse, all the galaxies streaming back together, the whole cosmos contracting toward a single dense point, a mirror image of the fiery birth it came from. This is the Big Crunch, and for much of the 20th century it was a favoured guess. A tidy, cyclical, almost comforting shape for time, a universe that breathes out and then breathes in. The discovery of the accelerating expansion is what pushed it to the margins. A universe quickening apart is not a universe preparing to fall back together. Gentler cousins of the rip exist as well, dreamed up by physicists exploring the spaces between these grand endings. In one, called the Little Rip, dark energy grows without limit just as in the Big Rip, but never quite reaches the finite moment of total destruction. The unbinding marches on forever, always tearing apart larger structures, never arriving at a single final instant. In another, called the Big Break, the expansion is brought to a sudden gentle halt by an unusual kind of energy, as though the universe pressed softly on a pedal and eased to stillness. Each of these is a different answer to the same question, a different shape for the far edge of time. The cosmos has handed mortal minds a whole fistful of possible endings and declined, so far to say which one is true. Step back from the endings and dwell for a moment on the strange privilege of the present. You're alive in what cosmologists sometimes call the stelliferous era, the star-filled age, the relatively brief chapter of cosmic history in which there are suns to shine and galaxies to wheel, and skies crowded with other lights to see. Before this chapter, the universe was too hot and too smooth for any of it. Long after, whichever ending arrives, the structures will be gone, scattered into the cold or torn into their pieces. The night sky as you know it, luminous and full of distant company, is a passing condition of the cosmos, not its permanent state. To look up at a sky still full of stars is to look up during the one act of the play in which the stage is fully lit. That privilege has a longer shape than a single sky. Astrophysicists who have mapped the deep future divide the whole life of the cosmos into great eras, and the star-filled one you inhabit is only the second of them. After the stelliferous age in something like 100 trillion years comes the degenerate era, when the last stars have burned out and only their cooling embers remain. White dwarfs, neutron stars, the dim cinders of suns. After that, on timescales so vast the numbers stop meaning anything, comes an age of black holes alone, and then a final dark era of thin drifting particles in an almost perfect emptiness. The bright busy present is the merest opening movement of a symphony, whose later movements are measured in numbers no clock could ever count to. Those numbers stretch the night a little wider without alarming it. 100 trillion years is the rough span over which stars will keep forming and shining before the gas to make them finally runs out. That is not a countdown to dread. It is a measure of how lavishly long the lit chapter lasts. The universe is less than 14 billion years old, which means the age of starlight has barely begun. It is still in its earliest morning, with thousands of times its present span still ahead, before even the slow ending of the stars sets in. Whatever fate waits at the far end, the cosmos is by every measure extraordinarily young, and so is the era of light you happen to have been born into. Here is a thought that has a tender edge if you let it settle rather than sharpen. Distance itself is the great isolator in this universe, and it works so gradually that it stays invisible within any single life. The Andromeda Galaxy, the nearest great spiral to our own, is bound to us by gravity, and is in fact falling closer, not away. The two galaxies may yet meet and merge billions of years from now, regardless of which cosmic ending lies beyond. Within a gravitationally bound group, the local rules of attraction still hold. Nearby companions stay near. It is only across the truly vast gulfs, out between the bound islands of stars, that the expansion does its unhurried widening work. The things closest to you are the things that stay. That approaching neighbour, seen up close, is one of the gentlest large facts in all of astronomy. The Andromeda Galaxy is some 2.5 million light-years away, and yet across that gulf it is falling toward us, drawn by gravity, closing the distance at a steady pace. Should the two great spirals one day meet, they would not collide the way two cars collide. They would pass through and around each other across hundreds of millions of years, two clouds of stars so sparsely spread that almost no single star would ever strike another. The spaces between suns are simply too vast. The two galaxies would merge and settle over an immense slow dance into a single larger galaxy. Even in a universe that may someday tear itself apart, the nearest large thing to us is not fleeing at all. It is coming home. The reason that local closeness survives while the far cosmos flees is worth holding gently in the mind. Gravity and expansion are not equals everywhere. They trade dominance with scale. Inside a bound system, a planet and its moon, a star and its planets, a galaxy and its neighbours held in a common group, gravity is already won, and the expansion of space has no purchase there at all. The dark energy that drives whole galaxies apart is simply too dilute across any modest distance to overcome a grip that is already closed. On every scale but the very largest, the universe remains a place of belonging. The widening happens only out past the edges of every embrace, in the great emptiness between the islands, where nothing is holding on. Far in the future of a forever expanding universe, the night sky of any inhabited world would tell a stranger and lonelier story than the one you can see now. The distant galaxies would have long since reddened past visibility and vanished beyond the edge of the observable. Any astronomers alive in that remote age, gazing out from within their own merged island of stars, would see only their own galaxy and the blackness beyond. No other galaxies anywhere. No evidence at all of the expansion or the dark energy that drove the rest away. The very history written across the sky tonight, the deep field crowded with thousands of distant galaxies in a fragment of dark no broader than the eye of a needle, would be erased from the heavens, unreachable and unguessable. You are living early enough to still see the company. That is not a small thing. There is a horizon out in the dark that no ship and no signal could ever cross, and it is worth understanding because it is the true shape of cosmic distance. Because faraway space expands faster than light can traverse it, there are galaxies whose light is already too far behind the swelling ever to reach us, and there are galaxies we can see tonight, glowing in old photographs that we are nonetheless already cut off from, their present selves forever beyond any message we could send. This boundary is called the cosmic event horizon, and an accelerating universe carries one wherever it goes. It lies roughly 18 billion light-years off in every direction. The more dark energy pushes, the closer that horizon draws inward, walling each observer into an ever smaller sphere of the reachable. The big rip seen in this light is simply the moment that horizon contracts past the very smallest scales. All through cosmic history, an accelerating universe quietly tightens the circle of what any observer can ever touch. In the gentle endings, the circle never shrinks below the scale of a galaxy. There is always at least your own home galaxy held safe within it. In the big rip, the circle keeps closing, past the galaxy, past the star system, past the planet, past the atom, until at the final instant it has shrunk to nothing at all. The same horizon that merely isolates each galaxy in the freezing future is the horizon that, in the tearing future, comes all the way home. One ending lets the circle rest, the other lets it close. Light itself carries the signature of all this stretching, written plainly in its colour. As space expands while a beam of light is crossing it, the light's waves are stretched longer right along with everything else, sliding from blue toward red, a shift astronomers can measure with great precision and read like a ruler laid across the cosmos. The farther the light has travelled, the more space has swelled beneath it, and the redder it arrives. This is how the most distant galaxies are weighed and dated, not by how bright they look, but by how far their colours have slid toward red. Reddening is the fingerprint of expansion, and it is everywhere in the sky, on every photon that has crossed any meaningful gulf to land at last on any glass. The oldest light of all carries the deepest reddening, and it fills the entire sky. Some 380,000 years after the universe began, the cooling cosmos first turned transparent and let its light fly free, and that light has been travelling unobstructed ever since. It set out as a fierce white-hot blaze, and across more than 13 billion years of expansion, it has been stretched so far that it now arrives as faint microwaves, cold, dim, only a few degrees above the absolute zero of temperature. This is the cosmic microwave background, the most ancient light it is possible to see, a whisper of the infant universe glowing softly in every direction at once. To detect it is to hold in an instrument the literal afterglow of the cosmos as a newborn. In any forever expanding universe, even that ancient afterglow has a quiet fate. As space keeps stretching across the immense future, the cosmic microwave background will redden and dim further and further, its faint microwaves drawn out toward longer and fainter wavelengths, until even this last whisper of the early cosmos thins away towards silence and slips below all possibility of detection. The newborn glow of everything would become in the deep future undetectable, a record erased not by destruction, but simply by being stretched too far to read. In a freezing universe, this fading is unimaginably slow. In a tearing one, it would be swift. But in every ending, the most ancient light trends the same way, toward a deepening, gathering calm. Return to the engine of all of it, the expansion itself, because there is a common misunderstanding worth setting quietly aside. The galaxies are not flying outward through space like fragments hurled from a blast, racing into some pre-existing emptiness. Space itself is what expands, new distance quietly appearing between things that are otherwise standing perfectly still. The galaxies are, for the most part, simply riding the growth of the space around them, carried along like leaves on a swelling tide rather than swimmers fighting through the water. This single idea dissolves nearly every puzzle about cosmic expansion. The galaxies are not running away. The ground between them is opening. That is also why the most distant galaxies can recede faster than light, without breaking any law of nature. Nothing is moving through space faster than light. It is space itself that is unfolding between here and there, and there is no speed limit on the stretching of the stage. A galaxy far enough away can have so much expanding space between us and it that the total distance grows faster than any beam could ever cross, which is exactly why its light can never reach us, and why it lies forever beyond the horizon. It is not outrunning light through space. It is being carried off by the growth of space itself, a thing no law forbids from happening at any speed at all. On the skin of a balloon, dots sit inked across the rubber, and a slow breath fills it from within. Every dot moves away from every other dot, and no dot is the centre. The centre, if there is one, lies off the surface entirely, in a direction the dots cannot even point. So it is with the cosmos. There is no place you could stand and call the middle of the expansion, no single point from which everything flees. From every galaxy the view is the same, all the others drawing away in every direction at speeds that climb with distance. Each observer sits at the apparent centre of their own receding sky, and every one of them is equally right and equally not the centre at all. It is a curious twist that the man whose simple proportion underlies all of this did not believe its boldest implication. When the equations of gravity first suggested a universe that could not sit still, one that must either expand or contract, but never simply rest, the natural response was disbelief, and a small fudge was added to the mathematics to hold the cosmos rigidly in place, an extra term invented for no reason except to forbid all motion. Then the galaxies were found to be fleeing after all, the universe revealed as anything but static, and the invented term was abandoned as an embarrassment. Decades later, that very same term came roaring back from exile, because it turned out to be the cleanest way to describe dark energy. The constant once added to stop the universe, and then thrown away in shame, is now a leading candidate for the thing that may one day end it. It is quietly humbling how often the cosmos has overruled its own best students. Each generation of astronomers has felt, briefly, that the broad outline was settled, a static universe, then an expanding one, then a decelerating one, then, against all expectation, an accelerating one. Every supposedly final picture has been a way station, a resting place mistaken for a destination. And so the big rip, like the big freeze and the big crunch beside it, is best held the way the cosmos itself seems to prefer being held. Lightly, provisionally, as one more honest guess in a long conversation that is nowhere near finished, and that none of those who began it will ever hear the end of. Turn now to how the strange number W is actually hunted, because it is one of the quietest detective stories in all of science. No instrument can measure dark energy directly. It gives off no light, casts no shadow, makes no sound. It can only be inferred from its effect, from the precise way the expansion has sped up and slowed across cosmic history, read off the dimming of distant exploding stars and the faint ripples frozen into the early universe. By gathering millions of galaxies and mapping exactly how they are arranged across billions of years, astronomers reconstruct the entire history of expansion and, from the subtle curve of it, read back the hidden value of W. They're reading the universe's fate out of the pattern of its past, the way you might read a river's strength from the shapes it has carved into stone. Hidden in the arrangement of those galaxies is a faint and beautiful ruler. In the first instant of the cosmos, sound waves rippled through the hot primordial fluid, and when the universe cooled and froze, those ripples left a preferred distance imprinted in how galaxies are spaced across the sky. A faint excess of galaxies separated by one particular span, the fossil echo of an ancient sound. That span has stretched along with the expanding universe, and by measuring how large it appears at different cosmic ages, astronomers can chart the entire history of growth with remarkable precision. It is a cosmic yardstick, frozen out of sound at the dawn of time and laid across the whole sky for anyone careful enough to read it. The newest of these grand surveys uses an instrument that drinks in the light of thousands of galaxies at once, capturing a wide swathe of sky in a single exposure and building the largest three-dimensional map of the cosmos ever made. Across years of patient observation, it charts the positions of tens of millions of galaxies, each one a faint beacon whose distance and motion add a single brushstroke to an enormous portrait of cosmic history. From that portrait, scientists hope to learn whether W is truly the steady negative one of a placid eternity, or a restless value that shifts, and whether it might lean, ever so slightly, toward the phantom realm below. The answer, when it finally comes, will be assembled patiently out of light, one distant galaxy at a time. The earliest hints from those sprawling new maps have stirred the whole field, because they point toward a dark energy that might not be perfectly constant after all, that might change gently over cosmic time. The signal is faint and far from settled, the kind of result that demands years more data before anyone fully trusts it. But the very possibility is electric. If dark energy is not a fixed and eternal constant but a thing that evolves, then the simple, comfortable picture of an unchanging vacuum tension would crack open, and the door to stranger fates, phantom realms, slow rips, surprises no one has yet imagined, would swing a little wider. The universe may be holding a card that no one has yet been dealt to see. The very name dark energy is younger than many of the people now reading these words by lamplight. It was coined only at the close of the 1990s, a fresh label for a freshly discovered mystery, chosen partly an echo of dark matter and partly as a frank admission of ignorance. Before then, the idea that empty space might push the cosmos apart was a fringe possibility most scientists set aside. Within a few short years, it became the dominant component of the universe, the master of its fate. A phrase barely older than a single human generation now names 2/3 of all that exists, a reminder of how swiftly the deepest pictures of reality can change. Measurements of the cosmos reveal that space, on the larger scales, is geometrically flat. Straight lines stay straight, and parallel beams of light neither converge nor spread apart over vast distances. This flatness is a delicate condition, finely balanced, and it tells astronomers a great deal about how much total energy the universe contains. The flat geometry, combined with the gentle acceleration, fits together into a single consistent picture, a cosmos filled mostly with dark energy, destined to expand without end. The shape of space and the fate of space turn out to be deeply linked, and reading the one helps reveal the other. There is a name for the moment the cosmos shifted from slowing to speeding. Astronomers sometimes call it the cosmic jerk, the point where deceleration gave way to acceleration as dark energy took command. It is one of the few genuine turning points in the entire history of the universe, a hinge between two great eras, the long early age of gravity's dominance and the long later age of dark energies. That such a turning even occurred and can be dated by careful study of distant exploding stars is remarkable. The universe did not simply expand at a single steady mood, it slowed, paused in its easing, and then began irreversibly to quicken. It is entirely possible that W is not a fixed number at all, but a value that wanders across cosmic time, and physicists routinely allow for exactly that in their models. Dark energy may have been subtly different in the distant past than it is today, and it may continue to change in the far future, strengthening, weakening, perhaps even crossing from the mild realm into the phantom one. Which way it leans would decide everything. The endings are not fixed destinations carved in stone, but possibilities that hinge on the behaviour of a single quantity that may, even now, be imperceptibly in motion. The future of the cosmos may still be deciding itself. Reflect for a moment on the audacity of even asking these questions from where we stand. A small, soft, short-lived creature on the surface of one ordinary world, around one ordinary star, has managed to measure the expansion of the entire universe, weigh the invisible energy that fills it, and trace the possible shapes of its ending billions of years hence. That such a thing is possible at all, that the cosmos is comprehensible to the minds it produced, is itself among the deepest wonders there is. The universe has, in a sense, grown, a way of looking at itself and wondering how its own story ends. You are part of that looking tonight as you rest. A quiet dignity runs through how provisional all of this knowledge remains, held honestly and without full certainty. Cosmologists do not claim to know how the universe ends. They map the possibilities, weigh the evidence, and wait for better light. The Big Rip is offered not as a prophecy, but as one carefully worked out branch among several, kept on the table because the numbers do not yet rule it out. This is science at its most graceful, comfortable with not knowing, patient for the answer, content to hold a vast open question without forcing it shut. And there is rest in that posture too, the permission to wonder freely, without needing to be sure. For all this beautiful machinery of measurement, the deepest fact about dark energy stays the simplest and the most astonishing. Nobody knows what it is. It might be the energy of empty space itself, a property of the vacuum predicted by the physics of the very small, though when that prediction is actually calculated, it comes out wrong by a margin so enormous it is often called the worst prediction in the history of physics, too large by a number with more than 100 zeros after it. It might be a new and invisible field threaded through all of space. It might be a sign that the rules of gravity themselves need rewriting at the larger scales. Each possibility points toward a different ending, and the gap between the theory and the measurement stands as one of the great unsolved puzzles of all of science. The scale of that secret widens the sky above you. The thing that makes up most of the universe, the thing that will decide whether everything ends in fire or ice, or a great unhurried tearing apart, is a thing for which there is not yet even a confirmed name, only a placeholder, only a question mark written across 2/3 of all that exists, and yet the night goes on exactly as it always has. The stars still rise, the unknown does not press upon the present at all. Whatever dark energy turns out to be, Whatever it will one day do, it does its slow work so far away and so far ahead that it leaves the here and the now entirely untouched, free to rest. Consider how genuinely, mercifully slow this whole drama is. At the present rate of acceleration, the time it would take the universe to double in size is measured in tens of billions of years. Whole civilizations could rise and fall and rise again. Whole species could evolve and vanish and be replaced, and the sky would look very nearly unchanged through all of it. The expansion is not a thing you could ever watch happen, the way you watch a tide creep up a beach. It is a thing you can only infer across spans of time so vast that a human life, a human history, the entire age of our kind, is less than a single grain of sand laid against it. The cosmos changes ceaselessly, but never on any clock a beating heart could keep. Here is a gentle paradox tucked inside the acceleration. Because faraway space is expanding faster and faster, the number of galaxies we will ever be able to reach, or even ever to see, is slowly shrinking. Galaxies visible tonight are one by one across the long ages, crossing beyond the cosmic horizon, their light losing the race against the swelling dark. The observable universe in this sense has already passed its fullest moment. We live near the high water mark of cosmic visibility, in an era when there is more out there to see than there will ever be again. Far future skywatchers will inherit an emptier heaven than ours. To be here now is to catch the universe very near the crest of its own brightness. A number can be put to that slow emptying, and it is strangely vast. In an accelerating universe, something on the order of 160 billion stars cross beyond the reachable horizon every year, slipping past the boundary of what any signal from here could ever catch. Not vanishing, not dying, simply passing forever out of touch. It happens far too gradually to notice, far too far away to mourn, and on a scale so enormous that the loss is purely a fact of arithmetic, not of feeling. Each year the reachable cosmos is a little smaller than the year before, and each year the sky overhead looks to any eye exactly the same as it always has. And yet, within the bounds of any single gravitationally bound system, none of this loneliness touches anything at all. The Earth and the Sun and its sibling stars, our galaxy and its small attendant galaxies, and the great spiral of Andromeda swinging slowly nearer, all of these are held fast by gravity in defiance of the expansion, and will be held no matter how the far cosmos behaves, right up until the very final moments of a rip, if a rip is even what comes. On every scale but the largest, the universe is still a place of company and belonging. The drawing apart happens only out in the dark between the islands, never within any one of them. What is bound stays bound, almost all the way to the end. There is a thought physicists have raised about the deep future that turns the loneliness into something almost tender. In a forever expanding universe, the very knowledge of the expansion would eventually be lost. The distant galaxies that reveal it would have vanished beyond the horizon. The ancient afterglow that records the hot beginning would have stretched and dimmed past all detection. Any minds alive in that far age would look out at a small, dark, apparently eternal cosmos, and have no way to know that it was ever otherwise, no way to discover the expansion, the dark energy, the fiery beginning itself. The truth of the universe's history is written across the sky in a kind of slowly disappearing ink. You happen to be reading it while the writing is still legible. That too is a quiet form of luck. Negative pressure does something so unexpected for a reason, and the reason lives at the heart of how gravity truly works. In everyday life, gravity comes only from mass. More stuff means more pull. But in the deeper theory, pressure gravitates too, and a strong enough negative pressure can flip the sign of gravity's effect, turning attraction into repulsion. Dark energy has exactly that strange property. Its pressure is profoundly negative, a kind of inward tension like a stretched rubber sheet, and a tension that great makes space push outward rather than draw together. The acceleration of the whole universe rests on this single counterintuitive truth. that under the right conditions gravity can shove instead of pull. Dark energy did not always rule the cosmos. For the first several billion years, ordinary matter held the upper hand, its combined gravity gradually slowing the expansion exactly as the early astronomers had expected. The universe was decelerating then, coasting outward but easing off. Only when space had stretched enough to thin the matter out did the steady tension of dark energy come to dominate, and roughly 5 or 6 billion years ago, the long deceleration reversed into a quickening. The acceleration is younger than the sun. For most of cosmic history, the brakes really were being pressed. The gas pedal is the recent development, and a big rip, if it lies ahead, belongs entirely to the universe's second half. That handover left a faint signature in the depths of the sky, a moment astronomers can actually locate in the distant supernova, the era when expansion stopped slowing and began to speed up. Look far enough out, which is to say far enough back in time, and the explosions trace a universe still decelerating. Look closer, and they trace one already accelerating. The crossover sits a few billion years in the past, a hinge in the history of everything, written in the dimming of dying stars. It is the precise instant the cosmic story turned from a long exhale toward an endless one, and it can be read, faintly, in light, that set out before the Earth was born. The timing of it all holds a curiosity that physicists find almost suspicious. Dark energy and matter happen to be comparable in their influence right now, in this particular cosmic epoch. Yet for almost all of the past, matter overwhelmingly dominated, and for almost all of the future, dark energy will. The two are roughly balanced only during a narrow window, and that window happens to be the one we find ourselves living in. Why now? No one knows. It may be pure coincidence, or it may be a clue to something deeper not yet understood. Either way, the very moment when the two great forces of the cosmos stand most evenly matched is the moment a wondering mind happened to open its eyes. Weigh how astonishingly faint dark energy is, drop for drop, and the wonder only deepens. Spread across the emptiness, its density is staggeringly low, the energy equivalent of just a few atoms of hydrogen in every cubic meter of space, fainter than the best vacuum any laboratory on Earth has ever made. Taken in any small volume, it is almost nothing at all. Its power comes entirely from its reach. It fills every cubic meter of an unimaginably vast cosmos, and all those near nothings summed across the whole add up to more than 2/3 of everything. The mightiest influence in the universe is also the most thinly spread. It rules not by intensity, but by sheer ubiquity. The simplest candidate for what dark energy is goes by the name of the cosmological constant, that steady, unchanging vacuum tension, the same in every place and every age. Under it, the universe drifts toward a particular far future state, physicists call de Sitter space, named for the astronomer who first explored it, an eternal, smooth, exponential expansion in which every galaxy beyond the local group has long since vanished beyond the horizon, and the cosmos becomes a nearly empty, ever-stretching void. That is the gentle ending, the one without a tear in it. The galaxies do not break apart, they simply withdraw, one by one, into an ever-deepening and ever-quieter dark, until each surviving island of stars is utterly alone. But the cosmological constant is not the only idea on the table. Some physicists imagine dark energy as a dynamic thing, a field spread through all of space whose strength can change slowly over cosmic time. They have given this hypothetical evolving energy a fitting name, quintessence, after the old notion of a fifth element beyond earth, water, air, and fire. Unlike a fixed constant, quintessence could weaken or strengthen across the ages, gently bending the fate of the cosmos one way or another. If dark energy turns out to be quintessence rather than a constant, then the ending is not yet written at all. It depends on which way the field drifts, and the universe keeps the final chapter open. The very word phantom attached to the most extreme form of dark energy, points to just how strange that form would be. A phantom field in the mathematics has a peculiar inverted property. Its energy behaves as though it runs the wrong way, a kind of negative twist that ordinary matter never shows. This is precisely what would let its density climb as the universe expands, instead of thinning out, and it is precisely why most physicists treat it with suspicion. Phantom energy may be only a mathematical possibility, a shape the equations can take, but the universe may never adopt. And yet it sits there, allowed, at the very edge of what the measurements permit, a ghost in the numbers that would, if real, bring everything to an end. Whatever dark energy is, its push reshapes the largest pattern in all of nature. The matter of the cosmos is not spread evenly. It is gathered into a vast structure astronomers call the cosmic web. Long, luminous filaments of galaxies strung across the dark, knotted together at great clusters and threaded around enormous, nearly empty voids. It is the largest pattern that exists, a froth of light and emptiness spanning the whole observable universe. Dark energy works upon this web by stretching the voids ever wider, pressing the filaments thinner, slowly draining the spaces between the strands. In a tearing future, even the strands themselves would finally come undone. Those great voids deserve a moment of quiet wonder all their own. Between the bright filaments of the cosmic web lie immense regions of near-perfect emptiness, hundreds of millions of light-years across, where galaxies are exceedingly few, and the dark goes on almost uninterrupted. These voids are the emptiest places in all of existence, and under the press of dark energy, they are slowly growing, swelling outward, claiming more and more of the cosmos for the dark. The future of an accelerating universe is, in a sense, the triumph of the voids, more emptiness, ever more thinly furnished with light, the bright web stretched into ever finer thread across an ever-expanding nothing. Consider how tightly the most stubborn structures cling together, and how long they would resist. A globular cluster, a dense ancient swarm of hundreds of thousands of stars, bound so closely that they wheel in a tight bright sphere, is among the most gravitationally compact families in any galaxy. Such a cluster would hold itself together long after looser structures had been pulled apart, resisting the rising tension down to the final stages of a rip. The tighter the grip, the later the loosening. In the great countdown, the most close-knit things would be among the very last to let go. A quiet rule that the firmest bonds endure the longest, true of stars and perhaps of more than stars. A profound difference separates the beginning of the universe from a big rip ending, and it lies in the direction of a strange mathematical edge. The Big Bang is what physicists call a past singularity, a point at the very start of time where the equations break down looking backward. A big rip would be a future singularity, a point at the end of time where the same equations break down looking forward. The scale of the universe, which began at essentially zero and has grown ever since, would in a rip race not toward the infinite slowly but toward the infinite suddenly, reaching it in a finite moment. The cosmos that emerged from one singularity might, in this one scenario, vanish into another, bookended by two places where the known laws fall silent. That growing scale has a name and a shape worth picturing. Cosmologists describe the size of the universe with a single quantity, the scale factor, which simply tracks how much space has stretched since the beginning. In an ordinary expansion, it climbs steadily. In an accelerating one, it curves upward, faster and faster. In a big rip, that curve would do something no other fate allows. It would shoot to infinity in a finite time, the size of the universe diverging completely at one fixed future instant. Every distance in the cosmos would become infinite at once, at the same moment, which is precisely what it means for everything, everywhere, to come apart together. The whole catastrophe is, in the mathematics, a single curve reaching up and never coming back down. The expansion rate itself would do the same, climbing toward the unbounded. The measure of how fast space is stretching, which today has a modest and gentle value, would in a big rip rise without limit as the final moment approached, slow at first, then quicker, then impossibly fast, racing toward infinity at the very end. It is this runaway of the expansion rate that does all the tearing. As it climbs, the scale at which expansion overpowers any given bond shrinks and shrinks, sweeping inward through clusters, galaxies, worlds, and atoms in turn. The whole drama, from the cosmic to the atomic, is one number growing too large for anything to hold against it. Modern astronomy has built whole missions devoted to pinning that number down, and they read like a roll call of patient ambition. Great surveys map hundreds of millions of galaxies to measure how the expansion has changed. A space telescope sweeps a third of the entire sky to trace the shapes of distant galaxies and the way their light is subtly bent. Another wide-eyed observatory will photograph the changing sky again and again, catching exploding stars by the thousands. Every one of these efforts is aimed at a single quarry: the value of W, and whether it sits at the mild negative one of eternity or somewhere stranger. The fate of all things is being pursued, methodically, one survey at a time. The dying stars that first revealed the acceleration are remarkable in their own right, a gift of cosmic regularity. They are a particular kind of stellar explosion that occurs when a dense stellar ember draws too much matter from a companion and detonates, and crucially each one flares to very nearly the same true brightness, like a row of identical lanterns scattered across the cosmos. Because their real brightness is known, their apparent dimness reveals their distance with great precision, which is exactly what let astronomers measure how the expansion had changed across billions of years. Without that strange uniformity, a standard candle built into the depths of certain stars, the acceleration and the whole question of the Big Rip might never have been found at all. The light from those distant explosions carries another quiet proof of expansion, hidden in its timing. An exploding star brightens and fades on a known schedule, a measured flickering that plays out over days, but the explosions seen far across the cosmos appear to unfold in slow motion, their rise and fall stretched out longer than they should be. This is expansion acting on time itself. As space stretches, it draws out not only the wavelength of light, but the very ticking of distant events, so that the faraway clock appears to lag behind. The stretched out fading of a distant supernova is the expansion of the universe made visible in the flow of time, a thing you could almost watch if you watched for long enough. For all the precision of these measurements, the expansion rate has lately become the subject of a genuine and unresolved puzzle. When astronomers measure how fast the universe is expanding by one method, reading the ancient afterglow of the early cosmos, they get one value. When they measure it another way, by carefully laddering up distances to nearby galaxies, they get a slightly but stubbornly different value. The two numbers refuse to agree, by more than the uncertainties should allow. This persistent disagreement is called the Hubble tension, and no one yet knows whether it points to some subtle error or to genuinely new physics lurking in the dark, perhaps even in dark energy itself, the very thing that shapes the ending. Pull far back, past every survey and every number, to the largest single fact a mind can hold. The observable universe is almost unfathomably vast, and it is only the part that can be seen. Light has had a little under 14 billion years to travel since the beginning, but because space has expanded all the while, the edge of the visible cosmos now lies some 46 billion light-years away in every direction, a sphere over 90 billion light-years across, filled with hundreds of billions of galaxies and possibly far more. And that is merely the portion whose light has reached us. Beyond it, the true universe may stretch on far further, perhaps without end. The Big Rip, if it comes, would reach into all of it at once. Within that immensity, picture the kind of image that captures it best. A long exposure of a patch of sky that looks, to the naked eye, entirely empty. Point a great telescope at such a blank scrap of darkness, a patch you could cover with a single grain of rice at arm's reach, and let it gather light for days, and the void fills with galaxies. Thousands of them, spirals and ellipses and faint smudges of newborn starlight, each one a city of countless suns, in a piece of sky most eyes would call nothing. Every direction you could point holds the same hidden multitude. The emptiness is an illusion of a glance too brief. The sky is crowded almost beyond counting in every patch, all the way down. That crowded depth is exactly what the far future would erase. In an accelerating universe, the day will come, unimaginably distant but certain in this scenario, when a telescope pointed at that same scrap of sky would gather light for days and find only darkness, every one of those thousands of galaxies having long since slipped beyond the reach of any seeing. The deep, rich, galaxy-filled image that astronomy treasures is a portrait that the universe will not always allow to be taken. You belong to the era when the picture can still be made, when the depth is still there to be found. That is a kind of inheritance, quietly enormous. Our own galaxy belongs to a structure so vast it was only mapped in recent years, and its name means immeasurable heaven. The Milky Way sits near the outskirts of an enormous supercluster of galaxies, a great basin of hundreds of thousands of galaxies, flowing together across more than 500 million light-years, all of them gently streaming toward a common region. It is among the largest structures known, a continent in the cosmic web to which our galaxy and all its neighbours belong. And in a big rip, structures on this immense scale would be among the very first to feel the loosening, their great slow streams of galaxies pulled apart long before anything nearer to home. The universe has no edge, no wall, no boundary anywhere, and this is one of the most quietly mind-bending facts about it. There is no place where the cosmos stops and something else begins, no shore at the rim of everything. Space simply continues, either without end or curving back upon itself like the surface of a sphere, so that travelling forever in a straight line would never bring you to a final edge. The observable universe has a boundary only because light has had a finite time to reach us, not because space itself stops there. A big rip, then, would not tear the cosmos towards some outer edge. It would stretch every part of an unbounded space away from every other part, everywhere, with no rim and no centre to it at all. It helps to anchor these enormous distances against a single familiar one, the light of the sun, which takes about 8 minutes to cross the gulf to the Earth. The sunlight warming a window now left the sun's surface 8 minutes ago. The sun you see is always the sun of 8 minutes past. From there the scale only grows. The nearest star beyond the sun lies 4 years away at the speed of light, the heart of the galaxy tens of thousands, the nearest great galaxy millions. Every glance into the sky is a glance into the past, the distance measured in how long the light has travelled. And in an expanding cosmos, the farthest of those lights set out so long ago that the things that sent them lie forever beyond reach. The cosmic web that dark energy slowly stretches is built of threads almost beyond comprehension in their length. The luminous filaments of galaxies that lace the universe together can run for many hundreds of millions of light-years from end to end, strung between great clusters like bridges of light across the dark, with vast, near-empty voids cupped between them. It is the largest pattern nature has ever made, a cosmos spanning lacework of galaxies and emptiness, shaped over billions of years by gravity gathering matter into strands. Dark energy works against this gathering, thinning the threads and widening the gaps, and in a tearing future, even these grandest of all structures, the bridges between the clusters would finally come undone. Something quietly moving lies in noticing that the largest structures and the smallest share the same fate in a big rip, separated only in time. The supercluster, vast beyond any human reckoning, and the atom, smaller than any eye could ever see, would both come apart, the one near the beginning of the final unravelling, the other at its very end. Between those two extremes lies every scale of structure the universe has ever built, each unbound in its turn. It is a strange equality. The vastest things and the tiniest things, the ancient continents of galaxies and the humble atoms in a hand, all meeting the same quiet ending, each at its appointed moment in the long unwinding. Even our own galaxy has a fate woven into all of this, gentle on the timescales that matter to a Big Rip. The Milky Way, the great barred spiral that holds the Sun and the Earth, and every star you've ever seen with your unaided eyes, would in the tearing scenario be unbound in the last few tens of millions of years before the end. Its hundreds of billions of stars, after ages of faithful orbiting, finally set adrift. Yet a date tens of millions of years before an end that is itself tens of billions of years away is so remote it scarcely qualifies as the future at all. For all the spans a human mind can truly feel, the galaxy is eternal, turning, holding its great slow wheel of light exactly as it does tonight. The Sun, too, has its own ending, and it is worth setting beside the cosmic one for the sheer difference in scale. In something like 5 billion years, the Sun will swell into a bloated red giant, swallowing the inner worlds, before settling at last into a slowly cooling ember, a fate sealed not by dark energy, but by the ordinary burning of a star running low on fuel. That local ending will arrive long before any Big Rip could. The world we stand on has a nearer horizon than the cosmos does, and there is an odd comfort in that ordering. The great tearing of everything, even if it is coming, waits politely behind 100 smaller, gentler endings, none of them tonight. Step into the very deep future of a universe that merely expands, and you find the cosmos passing through long, strange ages, each dimmer and stiller than the last. After the stars stop forming, the galaxies fade from brilliant whirls into dull red smoulderings, their brightest suns long burnt out, only the faint and frugal small stars lingering on. The smallest red stars are the great misers of the cosmos, hoarding their fuel so thriftily that a single one can shine for trillions of years, far longer than the universe has yet existed. The last starlight in the cosmos will come not from the great brilliant suns, but from these tiny, frugal embers, glowing faint and red across an emptiness almost beyond imagining, the final lamps left lit. Further still, in the degenerate age, even matter as we know it may not last. Physicists suspect that the proton, one of the basic particles at the heart of every atom, may not be truly eternal, that over a span almost impossible to write down, far longer than the present age of the universe multiplied by itself many times, protons might quietly decay, and ordinary matter dissolve from within. Whether this truly happens is unknown. It has never been observed, only theorized. But if it does, then in a freezing universe the structures would unravel anyway, in their own slow time, atom by atom from the inside, a far gentler unmaking than the sudden tearing of a rip, but an unmaking all the same. Black holes themselves would inherit such a universe, and even they would not endure forever. Through a subtle quantum process, a black hole imperceptibly radiates away its mass, glowing with a warmth almost too faint to name, shrinking across spans of time so vast they make every earlier age seem an instant, until at last, in the deepest future, even the greatest black holes evaporate entirely, releasing their long-held energy back into the dark. In a forever expanding cosmos, this would be among the final events of all, the last black holes winking out one by one, leaving behind only a thin haze of faint particles in an almost perfect emptiness. The freezing universe ends not with a tear, but with a fade so gradual it barely deserves to be called an end. The Big Rip stands apart from all these gentle fadings precisely because of its swiftness and its completeness. The freezing universe takes its leave over numbers of years with hundreds of zeros, structures unwinding so slowly that each age feels eternal. The Big Rip, by contrast, would arrive at a single fixed moment and unmake everything at once, from the cosmic web down to the atom, in a finite and nameable time. One ending is an endless, deepening dusk, the other is a sudden, total noon. That two such utterly different fates can both fit within what the telescopes have so far measured is among the most remarkable facts in all of cosmology. the universe keeping radically different endings in play, declining to choose. In a quiet way, the very darkness of the night sky already hints at expansion. An old puzzle once asked why the sky is dark at night at all. If the universe were infinite and eternal and full of stars, then every line of sight should eventually land on a star, and the whole sky should blaze as bright as the sun. Yet the night is dark. Part of the answer is that the universe is not eternal and unchanging. It had a beginning, and it expands, stretching and dimming the light of the most distant sources until they fade below seeing. The darkness between the stars is itself a clue, written across every night sky, that the cosmos is finite in age and growing. The dark is not empty of meaning. It is full of it. That same expansion is what isolates each galaxy into its own slowly closing world. In the far future of an accelerating universe, the local group, our own Milky Way, the Andromeda Galaxy, and their small attendant galaxies, all bound together by gravity, would merge into a single great elliptical galaxy, an island of stars cut off entirely from the rest of the cosmos. Beyond its edges, the dark would hold nothing visible at all, no other galaxies, no distant lights, only the merged home island and the empty night around it. Every gravitationally bound family in the universe would become its own such island, each one alone, each one unaware of all the others. The cosmos would become an archipelago of solitary lights, with seas of darkness no signal could ever cross. And yet, and this is the quiet mercy folded into even that lonely future, from inside any one of those islands, nothing would feel diminished at all. A galaxy is so enormous, so full of stars and worlds and slow-turning light, that an observer within it would never sense the absence of the vanished others. The home sky would still be crowded with suns. The great wheel of the galaxy would still arch overhead. There would still be more wonder in one home galaxy than any mind could exhaust in 1,000 lifetimes. Isolation, on the cosmic scale, does not mean emptiness up close. Even the loneliest far future galaxy would be, to anyone living within it, a sky brimming with light. Drift back now to the smallest end of the Big Rip, because there is a marvel hidden in the structure of matter itself that the rip would have to overcome. The atoms in your body, in the bed beneath you, in the ground and the air and the distant stars, are held together by forces of staggering strength relative to their size. The electric force binding an electron to its nucleus, and the nuclear force binding protons and neutrons into the heart of the atom, are among the firmest grips in all of nature. Grips that hold against heat, against pressure, against almost everything the universe can throw at them. For dark energy to pry them apart, the outward tension of the empty vacuum would have to grow stronger than the very forces that make matter cohere. That such a thing is even conceivable says something about how far the equations are willing to run. And here is the strange grace of those final fractions of a second. They would be, for any matter caught within them, utterly painless and instantaneous, beneath any possibility of being felt. The unbinding of an atom would happen faster than any signal could cross the atom, faster than any sensation could even begin to form. There would be no drawn-out suffering written into the physics, no long agony, no slow terror, only an unimaginably brief transition from structure to no structure, quicker than thought, quicker than the firing of a single nerve. If the cosmos ever does choose this ending, it has at least chosen a swift one. The very last instant would arrive and be over before anything could possibly know it had begun. It is worth resting on what makes the Big Rip unique among all the possible endings. It is the only one that breaks the bonds inside structures. In every other fate, gravitationally bound things stay bound. Galaxies hold their stars, stars hold their planets, atoms hold their parts, and the changes happen only in the great empty gulfs between them. A freezing universe pulls the islands apart but never touches what is inside them. A Big Rip is the single scenario in which the tearing reaches past the gulfs and into the things themselves, undoing not just the spaces between structures, but the structure's own grip on themselves. That is why it stands alone among the endings, and why it is the most dramatic of them by far. You yourself are not expanding, and it is worth understanding why, because it reveals exactly where the rip's strangeness lies. Your body, the chair, the Earth, the whole solar system, all of it is held together far too firmly for the present expansion of space to have any effect. The cosmos grows in the vast emptinesses between galaxies, where nothing is holding on. It does not grow inside a hand, a planet, or a star, where the bonds of matter and gravity easily win. Today, the expansion is a thing that happens only out in the great between spaces. The whole terror of a big rip is the idea that one day the expansion would finally reach inward, into the hand, the planet, the atom, where today it cannot reach at all. A quiet boundary surrounds our own small island of galaxies, beyond which the cosmos is already running away. The galaxies of the local group are bound to one another and stay together. But just past the edges of that bound family, the general flow of expansion takes over, and everything beyond drifts outward with the swelling of space. Our galactic neighbourhood is, in effect, an eddy of stillness in a vast outward current, a place where local gravity has carved out a small exemption from the universal drawing apart. Inside the eddy, the old companions stay close. Outside it, the whole rest of the cosmos is on its way to somewhere we can never follow. The contents of the universe sort into three great portions, and their proportions are themselves a marvel. Roughly 68 parts in 100 are dark energy, about 27 are dark matter, an unseen substance that clumps and pulls with gravity but emits no light, and only the remaining 5 or so are ordinary matter, the atoms that make stars and worlds and living things, everything that has ever been seen or touched. The visible cosmos, in other words, is the thin, bright rind on a fruit that is almost entirely invisible within. And of those 3 portions, it is dark energy, the largest and least understood, that holds the deciding vote on how everything ends. It helps to keep dark matter and dark energy clearly apart, because they are opposites in almost every way despite their shared adjective. Dark matter is a clumping, gathering thing. It pulls inward, helping to build galaxies and hold them together, a hidden scaffolding of gravity. Dark energy is a smoothing, scattering thing. It pushes outward, pulling structures apart and accelerating the cosmos. One assembles, the other disperses. They are the 2 great unseen hands of the universe, and they pull in opposite directions, and the entire shape of cosmic history is the slow story of which hand prevails, at which scale, and which age. Dark energy reveals itself in another subtle way, through the faint bending of a light across the sky. Mass warps the space around it, so the light from distant galaxies is gently deflected as it passes nearer ones, distorting their shapes by minuscule amounts. By measuring those tiny distortions across millions of galaxies, astronomers can map how matter is distributed and how the great cosmic structures have grown over time. And the rate of that growth is itself shaped by dark energy, which slows the gathering of structure as it pushes the universe apart. Even an invisible push leaves fingerprints if you know how to read the warping of light across enormous distances. Out at the very edge of the observable, a galaxy hangs poised on the cosmic horizon itself. From here, its light arrives ever more deeply stretched, more and more reddened, as though the galaxy were freezing in place at the boundary, its image lingering, dimming, fading toward red, never quite winking out but drawing ever nearer to invisibility. It is a strange and beautiful effect of an expanding cosmos. Things do not simply vanish from the horizon all at once, but seem to slow and redden and hang there, their final light stretched across enormous spans of time. The edge of the visible universe is lined with the faint reddening ghosts of galaxies caught forever in the act of leaving. The most distant galaxies ever glimpsed are seen as they were when the cosmos was barely a few 100 million years old. Their light has been travelling for more than 13 billion years to reach the present, stretched so far by expansion along the way that it arrives shifted deep into the infrared, invisible to any eye and detectable only by the most sensitive instruments. To look at them is to look almost all the way back to the first generations of stars, to the cosmic dawn itself. That such ancient, faraway light can still be gathered at all is a gift of timing. In a far future universe, this deep light will have stretched away entirely, and the cosmic dawn will be lost from the sky forever. The sheer count of those galaxies is among the largest numbers anyone has tried to attach to the cosmos. Careful surveys, extrapolated across the whole observable universe, suggest that it may contain on the order of 2 trillion galaxies, 2,000 billion separate cities of stars, each holding anywhere from millions to many hundreds of billions of suns. The number is so vast that there are likely more galaxies in the observable cosmos than there are grains of sand on every beach and in every desert on the Earth. And every one of those 2 trillion galaxies, in a tearing future, would be undone at the very same instant. The scale of what a big rip would unmake is, quite literally, beyond counting. There is a temperature to the universe as a whole, left over from its fiery birth, and it is astonishingly cold. The ancient afterglow that fills all of space sits today at about 2 7/10 degrees above absolute zero, barely a whisper of warmth above the coldest temperature that can exist, the lowest limit nature allows. Everything in the cosmos is bathed in this faint, even glow, the cooled remnant of a heat that once filled the whole young universe. As space keeps expanding, that temperature drifts lower and lower, the universe growing imperceptibly colder across the ages. The cosmos has been cooling since its first instant, and in every ending but a collapse, it goes on cooling toward an ever deeper chill. That same cooling is written into the wavelength of the most ancient light. When that afterglow first set out, the universe was a searing furnace, glowing white hot at thousands of degrees. Over more than 13 billion years of expansion, its light has been stretched by a factor of more than 1,000, sliding from a brilliant glare all the way down to faint microwaves. The reddening of that single light is one of the most direct measurements of how much the universe has grown. Space has expanded roughly 1,000-fold since that light began its journey. You can read the entire scale of cosmic history and how far one ancient beam has slid toward the red. Here is a curious fact. The edge of the observable universe is itself growing, even as galaxies slip beyond reach. Each year, light from slightly more distant regions has had time to arrive, so in one sense the visible cosmos expands. Yet because faraway space is accelerating away, ever more galaxies are also crossing beyond the point from which their light could ever reach us. The two effects run against each other, and in an accelerating universe the second one wins in the long run. The horizon of what we can see is, in the deepest future, a door easing shut, wide open now, in the bright early ages, and destined across unimaginable spans to swing gradually closed. Think of the loneliest astronomer who could ever exist, a mind in the far future of a forever expanding cosmos, born into a single isolated galaxy, with nothing visible beyond it. Such an observer would have no way to discover the expanding universe, no distant galaxies to measure, no afterglow left to detect, no evidence at all that the cosmos was ever anything but a single static swarm of stars in an eternal void. The grand truths that the present age can read so plainly, the swelling of space, the unseen energy driving it, the universe's blazing birth, would be utterly unknowable to them, erased from the sky. They would live in a smaller, simpler, more mysterious cosmos than ours, and never know what had been lost. The richness of the visible universe is a privilege of living early. By a kind of cosmic accounting, the present moment turns out to be extraordinarily favoured. The era when the sky's full of visible galaxies, when the afterglow is still warm enough to detect, when the expansion can still be measured, and the history of everything still read. This window is open now, and will not stay open. It opened when the first structures formed and the cosmos cooled enough to be transparent, and it will close in a forever expanding universe as the galaxies withdraw and the afterglow fades. You're alive inside the readable chapter of cosmic history, the one age in which the universe still tells its own story plainly to anyone who looks. That is a quiet and remarkable kind of luck. It is worth dwelling on just how gentle the present rate of cosmic expansion truly is on any human scale. Over the distance from here to the moon, the swelling of space adds an utterly negligible amount. Over the span of a single human life, even the gulf to a nearby galaxy widens by an amount that changes nothing anyone could ever perceive. The expansion only becomes mighty across the truly enormous distances between far-flung galaxies, where its small, steady fraction, multiplied by an immense gulf, finally adds up to a great speed. Up close, it is nothing. Far away, it is everything. And the Big Rip would simply be the day, ages hence, when the nothing up close finally grew into a something. There is a beautiful symmetry in how the rip would have to overpower not one force, but all of them in turn. The bonds holding the cosmos together come in different strengths and reach across different scales. Gravity binds the galaxies and worlds. The electric force binds electrons within atoms. The strong nuclear force binds the heart of every nucleus. A Big Rip would have to defeat each of these in its proper order, from the weakest over distance to the strongest up close. Gravity first, far out among the galaxies, and the nuclear force last, deep inside the atom. The countdown is, in a sense, a ladder of the forces of nature, climbed downward rung by rung, each one finally outmatched by the rising tension of space itself. A Big Rip would leave nothing behind. No embers, no remnants, no cooling ruins. The freezing universe ends with leftovers, cold dead stars, dim particles, the faint scattered ash of everything that was. A collapsing universe ends with a dense fiery point, perhaps even a new beginning. But a Big Rip would end with the very fabric of space torn beyond the scale of the smallest things, leaving not even atoms to scatter in the dark. It is the most complete of all the endings, a clean slate written by tearing the page itself. And yet, precisely because it is so total and so swift, it is also, in a strange way, the least sorrowful. There would be no long lingering ruin to mourn, only a sudden silent absence. Even gravity, the gentlest and most familiar of the forces, would in the final moments be outmatched by the expanding vacuum. And there is something almost poetic in that reversal. Gravity built everything. It gathered the first gas into stars, drew the stars into galaxies, knit the galaxies into the great web. For the entire history of structure, gravity has been the patient architect, pulling the cosmos into shape. In a Big Rip, the very expansion that gravity once shaped would finally overpower it, undoing in moments what gravity spent billions of years assembling. The builder, in the end, outdone by the room it built in. But that ending, if it comes at all, lies so far beyond every horizon of time that gravity will go on quietly building, undisturbed, for ages upon ages yet. One thought softens the whole idea of an ending. Nothing that ever happened would be unmade by it. A Big Rip, or a freeze, or any far future fate lies downstream of every moment that has ever occurred and ever will occur for ages. Every sunrise, every life, every quiet night like this one. The ending does not reach backward. It cannot touch what has already been. All the warmth and light and wonder of the long, bright middle of the cosmos will have genuinely happened, fully and completely, no matter how the distant story closes. An ending, however vast, only marks where the road stops. It does not erase the journey that came before it. The universe, for its part, gives no sign of urgency about any of this. The afterglow is still warm, the galaxies are still gathered. The expansion, though real, is so slow that across the entire span of human civilization the sky has not visibly changed at all. The same constellations the earliest stargazers named still hang very nearly where they hung. Whatever ending is coming arrives on a clock so vast that the whole of recorded history is a single unmeasurable tick of it. The cosmos is not racing toward its conclusion. It is taking its time, an almost infinite amount of it, and there is a deep calm in being a small part of something so utterly unhurried. The whole scale of cosmic time lies out like a single long road, and somewhere on it sits this very night. The road stretches from the fiery beginning, nearly 14 billion years back, and runs onward into a future that, in the gentler endings, has no visible end at all. Trillions upon trillions of years of slowly dimming stars and fading light. On that immense road, the present moment, the lit moment, the moment in which you are resting, sits almost at the very start, in the bright first stretch where stars are young and galaxies are full. Whatever ending waits, it lies impossibly far ahead, around bends in the road that no one alive will ever round. You're near the beginning of a very long and very gentle journey. A strange comfort lives in how thoroughly the far future would forget us and everything else. In a forever expanding cosmos, all records, all light, all evidence of the bright structured age would eventually stretch and dim past any possibility of recovery, not destroyed in any violence, simply spread too thin across too much space to ever be read. The universe does not keep a ledger. It does not hold on to its past the way a mind holds a memory. And yet this very forgetting is part of why the present is precious. The bright age does not last, is not preserved, cannot be revisited, which is exactly what makes being awake inside it now such an uncommon and specific gift. Hold one more time the central, steadying truth beneath all of these scenarios. Every single one of them lies further from tonight than the entire age of the universe lies behind it. The soonest plausible Big Rip is more than 20 billion years away. The likelier readings push any ending out to hundreds of billions of years, or trillions, or away past all reckoning. Against numbers like these, the difference between the various endings becomes almost academic. Not because the endings do not matter, but because every one of them is so unfathomably distant that none of them cast the faintest shadow on a single night now. The far future is real. It is also, from here, infinitely far away. One gentle paradox closes the great arc of the science before the night softens further. The expansion that might one day tear the cosmos apart once did the opposite work entirely. Long ago it cooled the searing early universe enough for atoms to form, for stars to ignite, for galaxies to gather and shine. Every structure that has ever existed owes its existence to the swelling of space. The same outward drawing that could one day be an ending was, in the beginning, the necessary condition for there to be anything at all. Creation and dissolution in this cosmos are written in a single continuous gesture. The long, slow opening of room, first making space for everything, and perhaps, unthinkably far ahead, making too much. Lift your gaze from the atom back to the whole, and notice the shape that all the endings quietly share. Whether the universe freezes or tears or against the odds collapses, the common thread running through every fate is a return to simplicity, a smoothing out, an undoing of structure, a long settling toward a state with less and less happening within it. The complex lit-up, structure-rich cosmos of the present is a temporary excitement strung between two simplicities, the smooth, hot uniformity of the beginning and the smooth, cold uniformity, or the scattered freedom of the end. You're alive inside the interesting middle, the brief, bright interval when the universe is busy being something in particular, rather than nothing in particular. Every star, every world, every watching mind belongs to that middle. It moves something in you to realize that complexity is the rare thing, the exception, rather than the rule. For the overwhelming majority of cosmic time, the long ages before structure ever formed, and the immeasurable ages after it dissolves, the universe is, or will be, a far simpler place than it is tonight. Stars, planets, oceans, the intricate chemistry that lets a thing wonder about its own ending. All of it is concentrated into a single thin slice of the whole timeline, like one bright band glowing in an otherwise dim spectrum. The very fact that there is something here, right now, complex enough to consider the Big Rip is itself a kind of cosmic coincidence of timing, a window that was not always open and that will not stay open forever. You found yourself awake inside it. Follow a single beam of starlight and let it teach you what distance does to time. The light from a distant galaxy left its source millions or billions of years ago. To see it at all is to see the past, the galaxy as it was, not as it is. By the time that light arrives, the galaxy itself may have changed beyond recognition, merged with another, scattered or rearranged. The night sky is not a snapshot of the present at all, but a vast layered collage of different ages. Nearby stars seen as they were a few years ago, distant galaxies seen as they were before the Earth even existed, all of it gathered together into a single apparent picture. You never see the universe as it is now, you only ever see where it has been. That delay grows stranger the deeper you look, and it folds quietly into the story of every cosmic ending. The most distant objects visible tonight are seen as they were when the universe was young, their ancient light only now completing a journey that began before the sun and the earth had formed. In an accelerating universe, the present selves of those far galaxies are already unreachable, already cut off behind the horizon, so that even as their old light still arrives, the galaxies themselves have in effect already left. To look deep into space is to look at faithful ghosts, real things, truly there once, whose now is forever beyond your reach. The sky is full of the patient light of places you can no longer ever go. There is a particular distance, far out in the cosmos, where the recession of galaxies reaches the speed of light itself, and it is closer than you might guess. Because the speed of a galaxy's retreat grows steadily with its distance, there comes a point, some 14 or so billion light-years out, where that retreat matches the speed of light, and beyond which it exceeds it. Galaxies past this line are receding faster than their own light can travel toward us, carried by the swelling of space. Yet, through a subtle quirk of an expanding cosmos, some of their ancient light still reaches us anyway, having set out long ago and ridden the changing expansion across the ages. The sky holds light from places that are right now moving away faster than light. The relationship between a galaxy's distance and its speed of retreat is so clean, it can be written as a single short rule. The velocity equals the distance multiplied by one constant number. Double the distance, and you double the speed of recession. 10 times the distance, 10 times the speed. This simple proportion, discovered nearly a century ago, was the first hard evidence that the universe expands at all, and it remains one of the most elegant laws in science. A straight line drawn across the cosmos, relating how far a thing lies to how fast it flees. Every fate of the universe, the Big Rip among them, is built upon that one plain line. A deep strangeness hides in the idea that empty space itself might hold energy, yet that is the leading explanation for the entire mystery. Quantum physics suggests that the vacuum is not truly empty at all, but seethes with faint, fleeting activity even where no matter exists. A restless background hum woven into the fabric of nothingness. If that vacuum carries even a tiny constant energy, it would push space apart exactly as dark energy does. The trouble is that when physicists try to calculate how much energy the vacuum should hold, the answer comes out vastly, absurdly too large. Closing that gap between the seething vacuum the theory predicts and the gentle push the sky actually shows is one of the deepest unsolved problems in all of physics. The actual measured value of that vacuum energy is so extraordinarily small that its smallness is a wonder in its own right. If the energy of empty space were even slightly larger than it is, the universe would have flown apart so violently and so early that galaxies, stars and worlds could never have formed at all. The cosmos would have been blown to a thin, cold mist before anything had time to gather. That dark energy is as faint as it is, and not stronger, is part of why there is any structure in the universe to begin with. The push that may one day end everything is mild almost beyond measure, and only that mildness, in the early ages, ever left room for anything to be built. There is a faint warmth even in the emptiest reaches of space, and it comes from that same ancient afterglow. Every cubic centimetre of the cosmos, no matter how far from any star, holds several hundred photons of that cold primordial light, a sea of microwave radiation filling all of space, left over from the universe's first transparent moment. In fact, these ancient photons vastly outnumber the atoms in the cosmos by something like 1 billion to 1. For every particle of ordinary matter, there are 1 billion leftover grains of light from the beginning. The universe is, by sheer count, far more a thing of light than of matter, and that light has been gently dimming and cooling through every age, in every fate but a collapse. The farthest thing it is possible to see is not a galaxy at all, but a wall of ancient light. Look in any direction, far enough, and you eventually reach the cosmic microwave background, the glowing surface from which the universe's first free light set out, beyond which no telescope can ever see, because before that moment the cosmos was opaque. It is a horizon made not of distance in space, but of distance in time, the edge of the visible past itself. Every observation of the deep cosmos ends at that same softly glowing wall, the same in every direction, the literal edge of seeing. And in a forever expanding universe, even that wall would eventually dim past detection, taking the visible edge of history with it. A Big Rip would, in one respect, be the most democratic event imaginable. It would arrive everywhere at once. There would be no single place where it began and spread outward, no wave of destruction racing across the cosmos. Because the expansion that drives it acts at every point of space equally, the final tearing would reach every galaxy, every world, every atom in the same instant, throughout the entire universe at the same time. There is no escaping to a safer region, because there is no safer region. The ending is woven uniformly into space itself. It is total, and it is simultaneous, and there is a strange even-handedness in that, a fate that plays no favourites and leaves no corner out. It is a quiet marvel that you cannot feel the expansion of the universe, even though you are immersed in it every moment. There is no wind from it, no sensation, no sign in daily life that the cosmos is swelling all around. The growth happens only when nothing is bound, far out in the gulfs between galaxies, while everything near and dear, your body, the ground, the air, the local stars, is held firmly in place by forces the expansion cannot touch. The grandest process in all of nature unfolds entirely beneath the threshold of any feeling. The universe is rearranging itself on the largest possible scale, and from where you lie, the night is perfectly, completely still. Astronomers describe how far the universe has expanded with a single, tidy number called redshift, written simply as a measure of how much a distant object's light has been stretched. A small redshift means a nearby galaxy, its light barely shifted. A large one means a remote galaxy, its colours slid far toward the red, and the ancient afterglow carries a redshift of over 1,000, the most stretched light of all. With one number, astronomers can place any object in cosmic history, near or unimaginably far. It is a kind of universal yardstick spun from colour alone, and reading it is how the entire timeline of expansion, from the first light to the present, was pieced together. There is something humbling in realising how young the galaxies were when their most distant light set out. The faintest, most remote galaxies astronomers can find were caught in the act of forming, when the universe was only a small fraction of its present age. Crude, bright, busy nurseries of the first stars, seen across nearly the whole span of time. Galaxies, it turns out, assembled astonishingly early, gathering out of the smooth young cosmos within its first several 100 million years. To trace their light back is to watch the universe build the very structures that a Big Rip would, ages later, undo. The long story of gathering, captured in light, running quietly toward an ending that may never come. Modern instruments have begun to weigh dark energy with a precision that would have seemed impossible a generation ago, and the early results carry a faint thrill of the unexpected. The vast new galaxy maps, when first analysed, hinted that dark energy might not be perfectly steady after all, that its strength might have changed ever so slightly over the eons. The hint is delicate, far from proven, the kind of signal that demands years more careful listening. But if it holds, it would mean the simplest picture is incomplete, and that the door to stranger futures, phantom realms among them, is not yet closed. The universe, it seems, is still keeping its final answer to itself, and may yet surprise everyone who studies it. Reflect on the fact that the question of cosmic fate is, in the long history of human thought, brand new and still wide open. Only within the last handful of decades has it become possible to ask, with real instruments and real numbers, how the universe will end, and the answer is still genuinely unknown, still being assembled, still capable of changing as new light arrives. You live in the brief and remarkable interval when the question has been opened but not yet closed, when the largest mystery about the future of everything sits, unresolved, on the desks of living scientists. To wonder about the end of the cosmos tonight is to wonder about something that humanity itself has only just learned how to wonder about. One consoling truth runs beneath all of this. The universe will go on being beautiful no matter which ending is true. A freezing cosmos cooling toward the dark is a thing of vast and tranquil grandeur. Galaxies glowing alone in an ever-deepening night, each a private cathedral of light. A tearing cosmos is a single, total, painless moment, swift beyond feeling. Even a collapse would be a return, a folding back toward a new fiery beginning. None of the endings is ugly, none is cruel. Each is simply the far, hushed closing of a story that has been unimaginably long and unimaginably rich, and every one of them lies so distant that the only thing it asks of the present is wonder. Picture the whole of it once more, held lightly, a universe that began small and hot, swelled and cooled, gathered itself into stars and galaxies and the great luminous web, and now drifts onward, accelerating gently into a future whose final shape no one yet knows. Somewhere in that future may lie a tearing, or a freezing, or a turning back. The numbers do not yet say which. But the story so far has been one of almost unthinkable creativity, emptiness giving rise to light, light to worlds, worlds to minds able to look back and trace the whole long arc. Whatever the ending, the middle has been a marvel. And you're alive, awake, resting in the bright heart of that middle right now. Think how recently any of this could be known at all. For nearly the whole of human history, the deepest questions about the universe's fate belong to myth and to guesswork. The sky a fixed dome, the stars eternal lamps, the future of everything unknowable in principle. The tools to actually measure cosmic expansion, to weigh dark energy, to follow the equations all the way to a big rip, are barely a century old, and some of the key measurements are younger than many people now living. You belong to one of the very first handfuls of human generations to hold any real evidence at all about how the cosmos might end. The questions are ancient. The capacity to begin answering them is brand new. Among those new answers is a humbling sense of proportion about our own place in time. If the whole history of the universe so far was squeezed into a single year, the entire span of recorded human history would occupy only the last fraction of the final second before midnight, and the universe's possible future, especially in the gentler endings, would stretch on for many, many more such years beyond. This present hour, the warm, wakeful, star-filled hour in which you are lying here, sits almost at the very beginning of cosmic time, not anywhere near its end. Whatever ending is coming, it is coming late, late, almost unimaginably late. The night you are resting in tonight is one of the early nights of the world. let the smallness of our moment be a comfort rather than a diminishment. To be a brief, warm, thinking thing near the dawn of an enormous and mostly empty future is not a tragedy at all. It is a rare and specific stroke of good fortune. The cosmos did not have to produce anything able to look up and wonder, and it did not have to do so during the one luminous chapter when there happened to be so much to look up at. You are matched to your moment with an almost improbable precision, alive while the stars still shine, awake while the sky is still full, conscious during the brief age when the universe is at its most richly furnished. Of all the times there are to be here, this is one of the very few worth being here for. Dark energy is sometimes described, half in jest and half in earnest, as a kind of anti-gravity, and the name fits better than it first appears. Ordinary gravity draws matter together. This strange energy of empty space does the opposite, driving everything apart with a steady, mild insistence. It is the only thing in nature known to push the cosmos outward against the inward pull of all its matter, a true counterweight to gravity itself, woven invisibly into every reach of the vacuum. The universe contains, in a sense, both a force that gathers and a force that scatters, and over the long arc of time, the scattering is by inches winning. There is no known force, no conceivable engine that could ever halt the expansion of the universe. It is not driven by anything that can be switched off or used up. It arises from the very nature of space, and it grows more powerful, not less, as the cosmos swells. Nothing within the universe could push back against it, because the push fills all of space equally and answers to nothing inside. Whatever ending lies ahead, it is not a thing that could ever be averted, even in principle, by any imaginable power. And there is a strange peace in that complete impossibility, the deep rest that comes from a thing entirely and forever beyond anyone's hands. The value of the expansion and the value of W together are sometimes thought of as the universe's destiny, written in 2 numbers. Pin them both down precisely, and the entire future of the cosmos follows, whether it coasts apart forever, or tears, or someday turns. Almost everything astronomers do at the larger scales, all the vast surveys and painstaking measurements, comes down in the end to reading those 2 quantities a little more sharply. The fate of all things, the whole shape of eternity, is encoded in a small handful of decimal places that the telescopes are still, even now, refining. Rarely has so much hung on so few digits. In the very far future of a merely expanding universe, the sky seen from any world would grow profoundly dark and empty over unimaginable spans, but not suddenly and not soon. The distant galaxies would withdraw and redden out of sight. The cosmos beyond the home island would fall silent and black. Yet within the home galaxy itself, stars would keep shining for ages beyond counting, and any sky beneath them would remain full of light. The emptying is a thing of the deepest future and the larger scales, never of the near and the now. Tonight, and for billions upon billions of nights to come, the sky stays exactly as generous as it has always been. Space itself can ripple, and that too is part of the fabric a big rip would tear. When great masses move violently, black holes spiraling together for instance, they send out faint waves through space-time, stretching and squeezing distance itself as they pass, ripples that instruments on Earth have actually caught. These gentle quakes in the fabric of the cosmos confirm that space is not a fixed and rigid backdrop, but a flexible, dynamic thing. The very flexibility that lets it expand, and that in the most extreme scenario could let it stretch without limit. Space bends to let a passing ripple through, and that same yielding quality, drawn out across the grandest scale, is what allows the whole universe to grow. It is worth holding the thought that the observable universe, vast as it is, may be only a vanishingly small part of the whole. Beyond the edge of what light has had time to reach us from, the true cosmos may stretch on enormously further, possibly without any end at all, far larger than the sphere we can ever see. The portion we can study is merely the part close enough for its light to have arrived. The rest is real but forever hidden. A big rip, were it to come, would reach into all of it, seen and unseen alike, everywhere at once. The smallness of our view is itself a lesson in humility. The cosmos is larger than the cosmos we can know. The discovery that the universe is accelerating has been confirmed since those first surprising supernovae by entirely separate lines of evidence that all agree. The faint patterns in the ancient afterglow, the spacing of galaxies across the sky, the slow growth of cosmic structure, each, measured independently, points to the same conclusion: a universe whose expansion is speeding up, filled with a dark energy that makes up most of its content. When several different windows onto nature all show the same strange thing, confidence grows that the strangeness is real. The acceleration, once a shock from a single kind of measurement, is now woven firmly into the whole picture of the cosmos. The Big Rip turns the usual fear of an ending on its head. Most imagined catastrophes are slow, drawn out, full of dread and struggle. This one, if it ever came, would be the opposite, preceded by billions of tranquil years in which nothing seemed wrong, and concluded in a final instant too brief for any sensation to form. There would be no long decline to endure, no slow gathering darkness to dread, only an immense peaceful interval, and then a single painless moment beyond all feeling. As endings go, it is among the gentlest the imagination could devise, however dramatic it sounds. The word doomsday is in its title, and yet there is nothing in it to fear. Everything genuinely beautiful about the present cosmos depends on its being caught between extremes, not too young, not too old, not too dense, not too empty. Earlier there were no stars. Later, in most fates, there will be none. The universe is structured and luminous and full of wonder only during a particular middle stretch, and the conditions that allow it are a kind of fortunate balance that will not last forever. To exist now is to exist within that balance, in the one era when the cosmos is rich enough to hold worlds and minds and the light to see them by. The Big Rip, like every ending, only marks the far edge of that lucky interval, an edge unimaginably distant from where you rest tonight. One final symmetry is worth resting on, between how the universe began and how, in this scenario, it might end. It started from a state where everything was unimaginably close together, packed into the smallest possible space, and it has been spreading outward ever since. A Big Rip would carry that spreading to its ultimate conclusion. Everything pushed infinitely far apart, the exact opposite of the crowded beginning. From maximum closeness to maximum distance, the whole history of the cosmos traced as one long opening out. The beginning and this possible ending would be perfect mirror images, one a gathering into a point, the other a scattering into the boundless, with the entire bright story of stars and worlds and minds unfolding in between. Notice that nothing about any of this requires you to do, decide, or remember a single thing. The fate of the universe will unfold exactly as it will, on a timescale beyond all imagining, entirely indifferent to whether anyone watches or understands or recalls it. There is no task here, no problem to solve, no danger to guard against. The largest story there is wants nothing from you at all, only perhaps that you let it widen the night a little, and then let it go. The cosmos has carried itself across an immensity of ages without your help, and it will carry itself onward for ages more, while you do nothing tonight but breathe and rest and sink a little deeper into the dark. Hold, last of all, the simple and steadying truth that the night sky above you is, by every measure, in the safest possible hands. It has held together for 13.5 billion years. It will hold together, near and whole, for billions upon billions more, far longer than any mind can stretch to imagine, long past the last generation that could ever descend from anyone now alive. Whatever distant ending waits, tearing, freezing, turning, It lies so impossibly far beyond every horizon of time that it casts not the faintest shadow on this one quiet night. The universe is enormous and old and gentle, and it is in no danger at all, and neither are you. Return once more to that famous countdown, but this time gently, from the inside, as a thought held at a great and safe distance. Imagine a world in the final months of a big rip, its sky already emptied of every other galaxy across the long ages, only its own sun and a few nearby stars remaining. For billions of years, nothing would have seemed amiss. Only the most attentive astronomer, noting that the far galaxies had reddened away one by one, would have known that anything at all was happening. The end, when it came, would arrive not as a long terror, but as a swift and final loosening. Months, then hours, then the briefest flicker of an instant. Far too fast at the very last to be feared. It is a doom, on paper. But it is a doom that asks for no dread, because it would be over before dread could form. And the deeper point is that it may never come at all. The Big Rip is the most dramatic of the possible endings, but very likely not the true one. The steadier reading of the data points toward the long, cold coasting apart, or, just possibly, toward something stranger still that no one has yet thought to imagine. To know that the universe might tear, and to know that it probably will not, and to be entirely at peace inside that uncertainty. This is the actual gift of the whole inquiry. The point was never to settle the ending. The point is the looking and the wondering and the quiet largeness that comes from holding so vast a question in so small a mind, without ever needing it resolved. Notice how a question of this size changes the proportions of everything smaller. Set against 22 billion years, or against 200 billion, the worries of any single day grow faint and harmless. The deadline, the disagreement, the thing left undone or unsaid, all of it is taking place inside a universe with an immensity of time behind it, and far more still ahead, on a small warm world circling an ordinary star in one arm of one galaxy among hundreds of billions. Nothing about that vastness makes you matter less. It only makes the heaviness lighter, and the urgency softer, and the night easier to sink down into. The cosmos is enormous, and patient, and in no danger at all tonight. There is a kind of restfulness that comes only from a fact too big to do anything about. You cannot hurry the expansion, you cannot slow it, you cannot tend it or worry it into a better shape. The fate of the universe is one of the very few things genuinely and completely outside your hands, unfolding on a scale so far beyond any effort that the only possible response to it is to let it be. And there is a deep release in that. The release of a burden you were never carrying, the permission to set down a thing that was never yours to hold. The cosmos will do as it does. Your only task tonight is to rest beneath it. Picture then the simplest possible version of the whole story, the one you could carry down with you into sleep. Space is growing. The growing is gentle and almost unthinkably slow, and might go on forever, or might one day quicken to an end so distant it lies past the very edge of the imaginable. Either way, the stars are out tonight. Either way, the sky is full. Either way, the things closest to you, the warmth of the room, the weight of your own breath, the small bound world that holds you, stay exactly where they are, held by forces no dark energy will trouble for billions of years to come. The far cosmos can do as it likes. Here, close in, everything is still. And here is one last wonder to rest on, the gentlest of them all. The very same expansion that might one day undo everything is the expansion that made everything possible in the first place. Without the swelling of space in the universe's earliest moments, matter would never have spread and cooled and gathered into stars. Without the long, slow widening ever since, there would be no sky with depth in it, no ancient light arriving from afar, no vast dark stage across which galaxies could wheel and shine and be seen. The growth that carries the cosmos toward whatever ending awaits is the very same growth that gave it a middle worth living in at all. The Big Rip, if it ever comes, would be the final word of a sentence whose first word was simply the gift of room enough to exist. So the great map of cosmic fate comes to rest in a single easy truth, light enough to fall asleep holding. The universe is mostly a mystery, most of it invisible, most of its story still unwritten, its ending unknown and likely to stay unknown for ages yet. It might tear, or freeze, or surprise everyone who ever studied it. But every one of those endings lies unfathomably far away, past more time than has ever yet passed, and not one of them changes the single thing that is true right now. The sky is wide and old and calm, and it has held together for longer than any mind can hold, and tonight it asks nothing of you but that you rest beneath it. The work of wondering is done now. There is nothing more to understand, nothing more to gather, nothing the night still needs from you. Let the questions loosen and drift apart the way the galaxies do without any effort at all, each one going its own way into the dark. Whatever stayed with you tonight is more than enough. Whatever slipped away was never yours to keep. If you are still here, still drifting at the soft edge of sleep, another quiet journey is already waiting for you on the screen, ready for whenever you want it, or never at all. There is no need to reach for it. There is no need to reach for anything now. You do not have to remember a single fact. You do not have to carry the numbers, or the names, or the shapes of any of the endings. Let them all go the way the far galaxies go, softly, into the dark, without a sound. The universe is enormous and unhurried and entirely at peace. So is this room. So is your breath, easing now, growing deeper and longer, like the long, quiet breathing of the cosmos itself. There is nothing left to do. There is nowhere left to be. The sky is holding. The room is warm. The night is wide and kind. Let your thoughts settle, one by one, like distant lights going quiet over a still horizon. Rest now. And now, 101 wonders are resting with you. Sleep now. Good night.